This is our second lesson video for today. And in the first lesson video, we looked at the graphs of y equals e to the x and y equals natural log of x. And in this video, we're going to go over transformations and how we would graph transformations of exponential and logarithmic curves. So the first thing I would like you to do is look at the transformations that I've listed here. These are already transformations we know from chapter 2, so you might just want to pause the video and look at the descriptions of what's happening to the function and then the movement that the graph would make. We do know a few additional transformations, but these are the ones that I'm focusing on today. So let's just pause and read through those and make sure we remember all that. Okay, so we have a few examples that I've written in blue, and basically the idea would be if you wanted to graph one of these, what you could do is think of the graph of the parent function and then what transformation took place. So if you wanted to graph y equals 2 to the x plus 3, you would think of what the graph of y equals 2 to the x looks like and then shift it up 3. If you wanted to graph y equals 1/3 to the x minus 4, you would think about what the graph of y equals 1/3 to the x looks like and then shift it down 4. If you wanted to graph y equals log base 4 of x minus 2, you would think about what the graph of y equals log base 4 of x looks like and then shift it to the right 2. If you wanted to know what y equals natural log of x plus 1 looks like, you would first think about the graph of y equals natural log of x, and then you would shift it to the left 1. If you wanted to know what y equals 2 times 3 to the x looks like, you would first think about what y equals 3 to the x looks like, and then you would stretch it vertically by a factor of 2. And if you wanted to know what y equals negative log of x looks like, you would first think about what y equals log of x looks like and then reflect it across the x-axis. So I'm going to go ahead and do 4 of these examples. And what I've done to save time is I graphed the parent function, and then I'm just going to show what I would do with the parent function to get the transformed function. So for number 1, we're graphing y equals 2 to the x plus 3, and for your notes, it would be a really good idea for you to pause and actually work your way through each of these 4 examples, write them in your notes. So the first thing we want to do is visualize y equals 2 to the x. And so that's exponential growth. And you'll notice that I have put the coordinates of a couple of the key points there. And then you'll notice I've also put the asymptote in. And we're going to shift that whole graph up 3. Now, since the whole graph is shifting up 3, the asymptote is also shifting up 3. So the first thing I would do is put the asymptote in place. And then I would take a couple of the key points and shift them up 3. So we have the point here 0, 1, shift it up to 0, 4. And we have the point 2, 4, shift it up to 2, 7. And then you can draw the curve. And having the asymptote there is really important because it gives you a boundary line to make sure you don't go too low. Okay, number 2. We're graphing y equals log base 4 of x minus 2. So what I've done is graph y equals log base 4 of x already. And it looks like my label got cut off a little bit. So I'll just write it again. This is the graph of y equals log base 4 of x. And what we're going to do is shift that whole thing to the right. Notice I already have the asymptote in place, so I'm going to start by shifting the easy for me to say. Start by shifting the asymptote 2 to the right. There we go. And then take a couple of key points and shift those points 2 to the right. So the point 10 is going to shift over to the point 30, and the point 41 is going to shift over to the point 61. And then use your asymptote as a guide so you don't go too far over, and you can draw that new curve. Okie dokie. Number 3. Graphing y equals 2 times 3 to the x. So I started with the graph of y equals 3 to the x and put in the asymptote and some key points, and then what I want to do is stretch it vertically twice as tall. Stretching it vertically is not going to move the asymptote, so just put that in the same place. And then stretching it vertically is going to double all of the y coordinates. So the point that was 0, 1, double the y coordinate, and now you have 0, 2. The point that was 1, 3, double the y coordinate, and now you have 1, 6. If you have room, you could do others, but if I double the point that has a height of 9, it's going to be a height of 18, and that's way up there. I don't think I can do that. So we'll just go with what we have, and there's our graph. And then problem number 4, y equals the opposite of log of x. And of course we know that log of x means the same thing as log base 10 of x. Okay, we can read that a little bit better now. Log of x means the same thing as log base 10 of x. And so I've gone ahead and I've drawn the graph of y equals log of x. And then I've labeled a couple of key points and drawn in the asymptote. And now what I'm going to do is reflect this across the x-axis. So reflecting it across the x-axis will not change the asymptote. So we'll draw that in, same place it was. And then the point 10 is still going to be at the point 10, but the point 10, 1 is now going to be at the point 10, negative 1. So everything has flipped upside down. So that's what that looks like. Kind of looks like logarithmic decay now. Okay, there we go.